In 90 seconds, 6 million people lost everything. Not to a bomb, not to an earthquake, to the sun. On March 13, 1989, an invisible wave from our nearest star crashed into Earth's magnetic field and collapsed the entire power grid of Quebec. No warning, no defense, just darkness for 9 hours in the middle of a freezing Canadian winter. That was a relatively small storm. The real question is what happens when a big one hits. Right now, we're living through the most active period of the sun in over 2 decades. Solar cycle 25 peaked in October 2024, with sunspot numbers far exceeding every prediction. And it's not over. In January 2026, Earth was struck by the most severe solar radiation storm since 2003. NOAA classified it as an S4 event, just one step below the maximum on their severity scale. The agency notified NASA, FEMA, airlines, and power grid operators to prepare for potential disruptions. Auroras appeared as far south as Florida, and here's the unsettling part. This was still nowhere close to what the sun is capable of producing. We need to talk about the Carrington event. On September 1, 1859, British astronomer Richard Carrington was sketching sunspots in his private observatory outside London when he witnessed something never recorded before, an intense white light flare erupting from the sun's surface. What he didn't know was that a massive wave of charged particles was already racing toward Earth at over 2,000 kilometers per second. Normally, such a journey takes 3 to 4 days. This one arrived in just 17 hours. When it hit, telegraph systems across North America and Europe went haywire. Operators reported sparks flying from their equipment. Telegraph paper caught fire. Some operators disconnected their batteries entirely and found they could still send messages, powered by nothing but the electrical currents the storm induced in the wires. The night sky lit up with auroras so bright that people in Cuba and Hawaii could read newspapers outdoors at midnight. But here's where it gets really interesting. The 1859 event didn't just affect telegraph wires, it created electrical currents in the ground itself. These currents, called geomagnetically induced currents, flow through any long conductor they can find. In 1859, that meant telegraph lines. Today, it means something far more critical: the power grid, high voltage transformers, undersea internet cables, the entire backbone of modern civilization. A 2013 study by Lloyd's of London estimated that a Carrington-class storm today could cause between $600 billion and $2.6 trillion in damage to the United States alone. That's not speculation, that's their actuarial assessment. The eastern and midwestern United States would be hit hardest because the bedrock beneath these regions is more exposed to induced electrical currents. In some areas, the field strengths would be enough to damage or destroy high-voltage transformers. And transformers are the problem nobody wants to talk about. These aren't household appliances you can buy at a store. High-voltage transformers are custom-built machines that weigh hundreds of tons and take 12 to 18 months to manufacture. There is no strategic reserve. If a severe solar storm takes out dozens of them simultaneously across multiple states, replacements would need to be built, shipped, installed. We're talking months to years of cascading blackouts. But there's something most people don't realize. The danger isn't just on the ground, it's in orbit. A new study calculated that if satellite operators lost the ability to perform collision avoidance maneuvers for just 2.8 days, a catastrophic chain reaction could begin. That's the new math of our crowded skies. Before mega constellations like Starlink, the grace period was over 4 months. Now, losing control for just 24 hours carries a 30% chance of triggering a major collision. One collision creates debris. Debris causes more collisions. This is called Kessler's syndrome, and it could effectively seal off low Earth orbit for generations. The European Space Agency ran simulations on what a Carrington-level storm would do to satellites. Their conclusion was blunt. It is a question of when, not if, and when it happens, no spacecraft safety will be fully guaranteed. So what are the odds? How worried should we actually be? Research analyzing the past 150 years of geomagnetic data found that severe superstorms occur about 42 out of every 150 years. The truly extreme events, Carrington-class storms, happen roughly once every 25 years on average. That doesn't mean one is guaranteed soon. It means the probability in any given year is around 4% for a severe storm and about 1% for a Carrington-level event. 4% per year sounds manageable, but compound that over a decade or two, and the numbers become uncomfortable. And this is where it gets personal. Think about what happens when the power goes out for more than a few hours. Water treatment plants stop running. Gas pumps don't work. Cell towers lose backup power within a day or two. Hospitals switch to generators that need constant fuel. ATMs go dark. Traffic lights fail. Refrigeration ends. The systems we depend on every day are not designed to operate independently. They're networked, interdependent. A failure in one sector cascades into others. The March 1989 Quebec blackout lasted 9 hours. Millions woke up to cold homes, dark streets, and stalled elevators. Schools closed. The Montreal Metro shut down during rush hour. The Carrington Event's geomagnetic storm raged for almost a week. There is some good news. After Quebec went dark in 1989, Hydro-Quebec spent over $1 billion hardening their grid. They raised trip levels on protection systems, installed series compensation on power lines, and built real-time monitoring. Other utilities around the world began similar programs. NOAA's Space Weather Prediction Center now monitors solar activity around the clock and can provide warnings of incoming storms, usually with about 15 to 45 minutes of advance notice for the most severe events. The question is whether 15 minutes is enough to protect transformers that take a year to replace, in a world where losing satellite navigation for a single day could strand fleets of vehicles and disrupt precision agriculture, shipping, and aviation. We've been lucky. The May 2012 Carrington-class eruption missed Earth by about 9 days of orbital rotation. If it had happened 1 week earlier, you'd probably remember exactly where you were when the lights went out. The sun doesn't care about our schedules. It doesn't know about our satellites, our stock markets, or our just-in-time supply chains. It's been doing this for 4.5 billion years. The only variable that's changed is us. If you lived through the 1989 Quebec blackout, or the 2003 storms that took out power in Sweden and damaged transformers in South Africa, you've seen a preview. The question isn't whether a Carrington-level event will happen again, it's whether we'll be ready when it does. What would you do with 72 hours of warning? That's the scenario planners work with. Drop your answer in the comments. Because somewhere on the sun right now, magnetic field lines are tangling, building pressure, waiting to snap. The universe reminds us on its own schedule that we're still very small,